Nothing in the universe ever truly rests. Not planets, not stars, not even the tiny atoms sitting quietly in your palm. Everything is always rotating softly, endlessly, as if the universe is locked in a slow, eternal dance. Tonight, we drift into that hidden rhythm, from the tiny quiver of spinning electrons to the colossal rotation of galaxies stretching across millions of light years. We'll explore how motion shapes reality itself, how spin gives structure, balance, and even life. And if this quiet journey brings you a moment of calm, I'm grateful you're here. A gentle like or a tap on subscribe is the simplest way to show these night stories matter to you. Let's begin with the first mystery. Part 1. Why nothing ever stops moving. Try to find something in the universe that's completely motionless. You can't. Not a pebble. Not a star. Not even the space between them. Everything from atoms to galaxies is in motion. Some drift, some rotate, some spin so violently their edges blur into pure energy, but nothing ever rests. This isn't poetry. It's physics. Uncompromising, universal, and absolute. Stillness is an illusion of perspective. The chair beneath you was spinning with Earth at around 1,670 kilometers per hour, circling the Sun at 107,000 kilometers per hour, while the entire solar system races through the Milky Way at over 828,000 kilometers per hour. And the Milky Way itself is moving toward Andromeda at 110 kilometers per second. Every atom in your body is moving with it all. An unbroken chain of motion stretching back to the birth of the cosmos. To understand why nothing can ever stop, we turn to one of physics' most elegant and ruthless rules, the conservation of angular momentum. It means that if nothing applies force to stop a spinning object, it keeps spinning. Simple. You've seen it everywhere. Planets rotating, a skater spinning. Faster by pulling in their arms, a neutron star the size of a city whipping around hundreds of times a second. When the skater tucks in their arms, their rotation speeds up for the same reason Earth spun faster as the early solar system collapsed into a tighter mass of gas and dust. Angular momentum isn't just motion, it's a memory, a record of how something began. Earth still carries the spin it formed with 4.5 billion years ago. That rotation hasn't ended, only slowed slightly through its gravitational dance with the Moon. This principle holds the universe together. It keeps planets in orbit, galaxies in rotation, and even gives electrons their quantum spinner, tiny whisper of the same rule, echoing at the smaller scales. As we look into the night sky, we witness countless spinning systems obeying this law. The Sun turns once every 27 days, while Jupiter completes a full rotation in under 10 hours, stretching wider at its equator because of its speed. That bulge about 4,600 kilometers larger across the middle than top to bottom is the scar of rapid spin. Stars, planets, galaxies, they don't rotate by accident. They inherit movement from what came before. The Milky Way takes about 230 million years to complete a single rotation, with stars, gas, and dark matter all moving together in one slow, coordinated swirl. Even far from home, motion continues. When Voyager 1 left the solar system, its tiny instruments still measured rotation as it drifted into interstellar darkness, a lonely reminder that even machines, made by human hands, obeyed the same cosmic rule. If motion ever truly stopped, the Balance between energy, inertia, and force would break. Angular momentum would disappear, and physics as we know it would collapse. But that has never happened. Every experiment from particle colliders to deep space telescopes points to the same truth. There is no absolute rest. Even electrons around atoms carry spin-on intrinsic property. Not physical rotation, but still bound by the same conservation law that governs stars and galaxies. The universe remembers how everything began, and it never stops moving. From the smallest scales of matter to the vast expanses of the cosmos, nature mirrors itself. Motion layered on motion, a fractal pattern of rotation repeating across existence. And when you trace that pattern all the way back to the beginning, to the moment the universe erupted into being, you find that motion wasn't invented. It was released. Tiny disturbances in the newborn universe created uneven pockets of density. Those regions collapsed under gravity, spinning faster as they tightened, conserving the motion they began with. They became the first swirling clouds of matter, the first galaxies, the first stars. The same rule that keeps Earth turning today was forged in that original turbulence. Strange, isn't it? The same principle that keeps a child spinning top balanced also shapes the architecture of galaxies. The same physics that keeps a satellite locked in orbit determines how the universe holds itself together on unimaginable scales. Everywhere you look, rotation acts as both law and language, quiet rhythm that balances chaos. Scientists sometimes call this cosmic spin the choreography of inertia. Every star, planet, and atom moves in strict agreement with equations that never rest. Newton's mechanics, Maxwell's fields, Einstein's space-time, more 10 conclusion. Motion never truly ends. Even if energy fades, direction remains. If we could step outside time itself and watch the universe from beyond its expansion, we wouldn't see a frozen snapshot. We'd see endless turning. Galaxies would look like glowing gears, transferring angular momentum across billions of light years. The entire cosmos, humming not with sound, but with the geometry of motion. So, when we say, nothing in existence is truly still, it isn't metaphor. It's confirmed by observation, theory, and experiment. Everything we see, everything we are, depends on motion. Without it, gravity couldn't sculpt structure. Magnetic fields wouldn't form, and matter itself wouldn't hold together. The conservation of angular momentum isn't just lit as the backbone of reality. Every spin, from electrons to galaxies, carries its signature. A reminder that motion is the universe remembering how it began. The same rotation that keeps Earth spinning also keeps you anchored, carried through space on a world that never stops moving. You are part of that momentum, always were, always will be. Part 2. How did the first spins begin after the Big Bang? Picture a universe with no stars, no planets, no light, only a roaring sea of particles and energy stretching infinitely. For a brief moment after the Big Bang, everything existed as a scorching plasma of racing hydrogen nuclei, electrons, and photons colliding at impossible speeds. But inside that chaos, something subtle began to appear. Tiny variations in densities smaller. Then 1 part in 100,000 formed within the hot plasma. These tiny differences, later mapped by satellites like Planck and WMAP, became the blueprint for everything that followed. Galaxies, stars, and the very first cosmic spin, WMAP revealed that the early universe wasn't perfectly smooth. There were tiny temperature differences, only about plus or minus 0.00 to Kelvin in the cosmic microwave background, the oldest light still bathing the universe from 13.8 billion years ago. These fluctuations showed that matter wasn't evenly spread out, and gravity used those imperfections to begin shaping structure. As denser regions collapsed under gravity, the conservation of angular momentum took over. In simple terms, when a cloud of matter contracts, it must spin faster because it cannot lose the rotation it starts with. That's where the first spins emerged, not from any external push, but from gravity and conservation working together. NASA called this the first whisper of structure in a universe that was nearly silent. Those whispers evolved into swirling pockets of plasma, rotating faster as gravity tightened them. At first, the motion was random, directionless, but slowly, patterns formed. Dense regions pulled in nearby matter, creating the first clusters of baryonic normal matter, the universe's first storms of rotation. Around 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to merge into neutral atoms. Photons, no longer trapped by constant scattering, finally traveled freely, forming the cosmic microwave background radiation. The Planck mission later mapped this ancient light, revealing detailed patterns, each patch representing regions of different density, and inside those variations, spin took hold. Denser patches collapsed faster, converting falling motion into rotation through a process called vorticity generation. As matter fell inward, slight irregularities caused it to twist. That twist became cosmic spin. Planck's results showed that the early universe already contained the seeds of rotation. Pressure and temperature differences created flowing streams of matter that curled like invisible whirlpools stretching across space, even at enormous scales. The same laws applied. The same physics that stabilizes a spinning gyroscope guided the evolution of galaxy clusters. As baryonic matter clumped together, gravitational collapse converted potential energy into motion. Some became disorderly turbulence, but a fraction solidified into rotational momentum. Over millions of years, random currents organized into spinning flows. Simulations like JWST and the Millennium Run visualize this process, showing tiny vortices of early plasma growing into rotating protogalaxies, spanning tens of thousands of light years. Every simulation reveals the same truth. Where there is asymmetry, rotation appears. These first cosmic spins emerged less than 1 billion years after the Big Bang, before the first stars shone. The universe already held the momentum that would define everything after. Dense regions collapsed into spinning halos of gas, forming the earliest galaxies around redshift c, approximately equals 10 to 15. Roughly 13.3 billion years ago. This process is known as tidal torque theory. Forming protogalaxies twisted each other through mutual gravitational forces, increasing spin and aligning motion along cosmic filaments. Gravity didn't just pull it. Twisted dot observations today support this. Surveys like STSS show galaxy spins align with the large-scale structure of the universe filaments of gas and dot. Dark matter stretching across hundreds of millions of light years. These patterns trace back to those first uneven motions in the AE, Primordial plasma. Throughout cosmic history, angular momentum has been preserved, not destroyed. Gas clouds merging pass on their spin. Galaxies colliding exchange their rotation. The entire cosmic web acts like a vast network of rotating masses, conserving ancient momentum. Order emerging from chaos, structure rising from turbulence. The same law shaping everything from atomic spin to galactic rotation. As physicist Brian Greene notes, the laws of motion are universal, but their results are written differently across the cosmos. Observations of galaxy rotation since the 1970s show every orbit traces back to those early fluctuations. Even dark matter halos, silent and invisible, carry ancient angular momentum. The Planck mission estimated primordial density variations were around 10. That tiny imbalance, 1 part in 100,000, was enough to sculpt the entire universe. If things had been perfectly smooth, gravity would have had nothing to shape and no rotation could exist. Reality would be static, structureless, silent. But the universe was imperfect, and that imperfection is why everything moves. Spin was born. From imbalance. Matter didn't simply fall, it learned to turn. Every orbit, every spiral, every rotation from electrons to galaxies is an echo of those early disturbances. The same turbulence still resonates within us. In atoms forged from ancient spinning clouds, WMAP and Planck gave us a fossil snapshot of these earliest motions. The oldest light in existence carries subtle directional pattern signatures of early rotational fields. The European Space Agency called it the fossil record of the universe's first motions. That record is everywhere in spiral galaxies, in cosmic filaments, in the Milky Way's rotation. One full turn every 230 million years, still conserving momentum from 13 billion years ago. So when you look at the night sky, you're seeing ancient motion frozen in light. Those first subtle ripples became a permanent habit of the universe. To spin, to rotate, to move forever. From plasma to galaxies, the rule never changed. Motion comes from asymmetry, symmetry. Every moment you sit still, the earth beneath you spins relentlessly through space, moving faster than 1,670 kilometers per hour at the equator. You don't feel it, and there's no sound to remind you, yet the planet never stops turning. That constant motion isn't something Earth chose. It's something it inherited from the moment it formed, an ancient imprint stretching back to the birth of the solar system. Around 4.6 billion years ago, long before Earth existed, everything in our cosmic neighborhood was part of a vast rotating cloud of gas and dust known as the solar nebula. It stretched across unimaginable distances, made of hydrogen, helium, and the remnants of stars that died long before the sun was born. Within that cloud, gravity slowly gathered matter into clumps. As the cloud collapsed inward, its rotation accelerated a direct expression of angular momentum, the same principle. That makes ice skaters spin faster when they pull their arms in. What began as a slow drift became a sweeping, swirling rotation. The center grew hotter and denser, forming the sun, while the remaining material flattened into a rotating disk where planets formed. Inside that disk, particles collided and fused into larger bodies called planetesimals, each carrying a piece of the nebula's spin. Over millions of years, these objects merged to form early Earth, and with every impact, every fragment added its own tiny momentum. All those contributions combined into a single global rotation stabilized by the same conservation laws that shaped the solar system. Since then, nothing has been strong enough to stop Earth from spinning. According to NASA, the planet completes one full rotation every 23 hours, 56 minutes, and 4 seconds, sidereal day measured so precisely that even millisecond variations are recorded by atomic clocks. The only major force slowing Earth's spin is the Moon's gravitational pull, a detail explored later. During formation, colossal collisions helped shape how Earth spins, including a dramatic impact roughly 4.5 billion years ago when a Mars-sized object struck the young planet, tilting its axis and throwing material into space that later formed the Moon. Once Earth cooled and solidified, its rotation settled into the rhythm we know, sustained by the mass and inertia of rock, ocean, and metal at the equator. The surface races eastward at nearly 1,670 kilometers per hour, while the speed decreases toward the poles, reaching zero at Earth's axis. This is why rockets launch near the equator. They gain a natural boost from the planet's rotation, adding roughly 460 meters per second to a rocket's speed, according to the European Space Agency. But the true reason Earth continues rotating is simpler. Space offers almost no resistance. Beyond the atmosphere, there is no friction and no force strong enough to drain Earth's angular momentum, allowing the motion to continue nearly unchanged for billions of years. The same principle keeps spacecraft like Voyager spinning to maintain stability in deep space. Models of planetary formation show that all planets inherit their spin from the rotating disk that formed them, while collisions and gravitational forces determine each world's specific speed and tilt. Earth ended up with a balanced rotation, not too fast, not too slow. If it spun much faster, the equator would bulge dramatically and geological stability could break down. If it spun slower, days could last weeks and temperatures would swing brutally between light and darkness. Our 24-hour cycle is a product of cosmic balance. Other planets reveal this story in extremes. Jupiter spins so fast it completes a day in under 10 hours, causing a massive equatorial bulge. Venus spins slowly and backward, taking 243 Earth days to turn once. Earth sits in the middle of a steady rotation that shapes oceans, winds, seasons, and climate. Its axial tilt of about 23.5 degrees gives us seasons and long-term climatic stability. Sunlight heats air and water, winds flow across the surface, and yet none of this significantly alters the planet's fundamental rotation. Only the gradual pull of the Moon and Sun slows it over vast timescales. Evidence from ancient coral fossils and tidal sediments shows that hundreds of millions of years ago, Earth's day lasted about 22 hours. Tidal friction has been transferring rotational energy to the Moon's orbit for eons, causing Earth to slow while the Moon drifts away by roughly 3.8 centimeters per year confirmed through laser. Measurements conducted since Apollo missions placed reflectors on the lunar surface. Despite this gradual deceleration, Earth's total angular momentum remains conserved, shared between planet and Moon like partners, exchanging momentum in a slow cosmic dance. If we trace time backward, the rotation quickened shorter days, faster sunsets, stronger tides. The same primordial spin that began in a collapsing cloud of gas still drives day and night. Ocean currents and the cycle of light and shadow that shapes life on Earth Angular momentum is the planet's silent engine, a thread connecting ancient cosmic history to every moment of today. Born before Earth had continents or oceans, this rotation will continue long after humanity is gone unless some unimaginable force brings it to a halt. A sunrise is not the sun rising. It is Earth turning toward the light. A sunset is not the sun falling. It is the world continuing its ancient spin, honoring the motion written into its beginning. The International Earth Rotation and Reference Systems Service maintains atomic timekeeping to synchronize with this natural variation. When Earth's rotation slows slightly, scientists occasionally add a leap second to Coordinated Universal Time (UTC), a subtle correction that keeps our clocks aligned with the planet's actual motion. It's extraordinary to consider. Our concept of time, the seconds we count, the hours we live by, is tied directly to the physics of a slowing Earth. Every millisecond gained is recorded in the structure of our timekeeping systems. The very definition of a day is gradually changing, one fraction at a time. In this cosmic exchange, there are no catastrophes and no adversaries, only balance. The loss of Earth's rotational speed is not destruction, but a graceful transfer of motion between gravitational partners. The Moon gains what Earth gives, and both evolve together, locked in a relationship that shapes the rhythm of our world. As Carl Sagan once said, the Earth is a very small stage in a vast cosmic arena. Yet even on this small stage, the slow exchange of angular momentum determines the dance of the heavens. This process is not unique to Earth. Across the solar system, astronomers observe similar tidal interactions. Jupiter's moon, Io, is heated internally by tidal friction from Jupiter's gravity, driving continuous volcanic eruptions. Saturn's moon, Enceladus, experiences tidal flexing that powers its icy geysers. Everywhere we look, gravitational tides transform motion into heat and spin into orbital energy, echoing the same law that slows our planet. As Earth's days grow imperceptibly longer, what we witness is the unfolding of a universal principle. The rotational energy that once kept Earth spinning faster now propels the Moon farther away. The same conservation laws that govern collapsing stars and orbiting galaxies govern our tides and sunsets. The universe favors balance, not direction. Though silent, the story of Earth's slowing rotation is written across time itself, captured in tidal sediments. Atomic clocks, laser reflections from the Moon, and the faint pull of gravity shaping oceans and skies. Even the calm of a quiet night is the echo of motion traded gently between two worlds. For Earth, the effect is incredibly small, so subtle it required one of the most precise experiments ever conducted to measure it. But around a spinning black hole, the effect becomes overwhelming, twisting light orbits, and even time itself. Let's start with Earth. In 2004, NASA launched Gravity Probe B, a satellite designed to measure both the curvature and the rotation of space-time around our planet. Inside were 4 gyroscopes, polished to within 40 atomic layers of perfect roundness, spinning freely in orbit to detect changes in the direction of space itself. If space-time were completely static, those gyroscopes would have pointed in the same direction forever. But they didn't. Over the course of a year, they drifted by about 39 milliseconds, exactly as Einstein predicted. NASA called it a milestone, proof that Earth's rotation tugs on spatomy. To grasp how small that is, Imagine measuring the thickness of a sheet of paper from 200 kilometers away. Yet even that tiny shift proved Earth leaves a subtle twist in the fabric of reality. The math behind this phenomenon is encoded in the Kerr metric, derived in 1963 by New Zealand mathematician Roy Kerr. Unlike the Schwarzschild solution, which describes non-rotating masses, the Kerr solution describes how rotation reshapes spacetime itself. Instead of a simple spherical curve, the geometry becomes a swirling funnel. Dragged into motion by spin near extremely dense and rapidly rotating objects, this effect becomes extreme. Around black holes, it forms the agosphere region outside, the event horizon where spacetime itself is forced to spin. Inside it, nothing can remain motionless. Matter is swept along by spacetime's rotation. This effect is so powerful, it may pull energy from black holes, a process called the Penrose mechanism. Observations from NASA's NuSTAR and Chandra missions have detected radiation consistent with this energy extraction. Even though Earth's frame dragging is subtle, it's always present. Every satellite feels a small correction from it. Without accounting for this, GPS and spacecraft navigation would drift over time. Our global systems work because they align with Einstein's equations, but around more extreme objects, the effect becomes dramatic. Neutron stars' city-sized bodies spinning hundreds of times per second warp spacetime so intensely that rotation and time dilation blur together. NASA's XM, M Newton, and NICE missions have measured shifts in radiation from matter falling into these stars, evidence of strong relativistic spin. In such environments, motion literally bends light, and even the meaning of a straight line changes. The Kerr solution also predicts that rotation changes the shape of a black hole's event horizon. Like planets, rotating black holes bulge at the equator and flatten at the poles. Inside, the geometry becomes so distorted that time and space can exchange roles, forming a landscape that still challenges physics. As physicist Kip Thorne once said, to understand a rotating black hole is to understand the whirling of spacetime itself. The Event Horizon Telescope's 2019 image of the black hole in Galaxy M87 confirmed this visually. The glowing ring wasn't perfectly symmetrical, its light was bent and distorted by the black hole's spin. The surrounding plasma moved along curved paths shaped not just by gravity, but by spacetime's rotation. Future missions like LISA launching in the 2030s will study gravitational waves from merging black holes. These waves carry the imprint of spin, revealing how rotation alters the frequency and shape of the signal. So what happens when spacetime rotates? The rules of motion shift. Directions curve. Light no longer travels straight. The idea of standing still stops making sense because, in a rotating spacetime, nothing can remain fixed. NASA uses a simple analogy. Place a marble on a flat trampoline and it rolls straight. Twist the trampoline while it rolls and its path curves. That's what rotating spacetime does to planets, light, and matter. This effect also shapes accretion disks, the vast spirals of gas around black holes and neutron stars. The inner regions of these disks are forced into motion by spacetime itself. Observations from JWST and Chandra show ion emission lines that shift due to frame dragging, allowing scientists to measure black hole spin. Some black holes rotate near the theoretical limit, defined by the Thorne limit, A equals 0.998, meaning the event horizon moves almost at the speed of light. In such environments, frame dragging dominates completely. Space and time become a rotating continuum spiraling inward. Even our sun produces tiny frame dragging effects detectable through high-precision measurements. Every motion of mass leaves a faint twist in space-y. In general relativity, this twist is not a metaphor, is literal curvature written into the math. Space-time isn't a static stage where events unfold. It is dynamic, reshaped by motion and energy. The faster something spins, the more it stirs the structure around it. Frame dragging unifies two truths. Motion and geometry are inseparable. To move is to curve space-time. To spin is to twist it. Every gyroscope in orbit, every photon near a black hole, every gravitational wave across the universe confirms that rotation is woven into existence itself. And that fabric, forever twisting and shifting, still holds mysteries we've only begun to understand. You drift beyond the familiar rim of the Milky Way, where starlight thins into silence. Far outside the shining disk, an immense, unseen sphere surrounds the galaxy, a quiet halo stretching many times farther than the furthest star you can see. Out here, gravity doesn't glow. It whispers. It shapes the arc of every spiral arm, guides each orbit, and holds the galaxy steady across billions of years. Modern telescopes, even the James Webb Space Telescope, now peer back to some of the earliest galaxies born after the first dawn of stars. And astonishingly, even those ancient systems already spin in stable disks. Researchers analyzing these early cosmic structures have concluded that their invisible halos must have formed early, acting as scaffolding long before the galaxies themselves settled into motion. You can trace this hidden mass not by sight, but by movement. When astronomers chart how fast stars orbit as distance increases, classical physics predicts a slow decline. Instead, every measured galaxy, from small, faint systems to giants like Andromeda, shows nearly constant orbital speeds. Flat curves, not falling ones, a signature of something unseen wrapping each galaxy in gravity. Dark matter reshaped modern astrophysics because without this extra mass, galaxies wouldn't hold together at all. With it, their motion suddenly makes sense. Some researchers have suggested that gravity itself may behave differently at vast scales. Modified Newtonian models, new extensions to relativity, yet none have matched the precision of dark matter. When tested across many fronts, galaxy clusters, gravitational lensing, relic radiation from the early universe. One astrophysicist summarized it simply: dark matter isn't a placeholder for ignorance. It is evidence that the universe contains far more than we detect directly. It's humbling to realize that the Milky Way spins, not because of the stars we see, but because of mass we cannot yet identify. Every circuit of the sun around the galactic center, every twinkling arc of stars above you, owes its permanence to an invisible halo surrounding us. It binds everything together, though its true nature remains unknown. Deep underground laboratories wait for the faintest particle interaction. Orbital observatories scan the sky for subtle signals. Every year, instruments grow more sensitive, listening for a whisper from the darkness that has shaped the cosmos since its birth. When the first compelling evidence emerged, many resisted the idea that most of the universe lies beyond perception. Yet decades later, nothing has overturned the original observations. Galaxies spin too fast. The unseen keeps them whole. So when you gaze up at the delicate band of the Milky Way stretching across the night, remember that the luminous stars are rapine, only the surface. Beneath, an unseen majority, roughly 85%, holds each orbit in place, cradling the spiral in silence. Spin has revealed what light alone could never show. Motion exposes structure. Rotation unveils the hidden. Now you drift deeper into the cosmos, toward a question rooted not in galaxies but in the limits of nature itself. How fast can something spin before the laws of physics begin to fail? There is a boundary for every rotating object, from the smallest atom to the greatest star. Gravity pulls inward. Inertia pushes outward. As long as inward forces prevail, matter remains whole. Push the speed too far, and the structure collapses. This is the razor-thin edge where rotation challenges existence. Begin with one of the most extreme objects in the universe, a neutron star. Born from the remnants of massive stellar explosions, each is no larger than a city, yet contains more mass than the Sun. Just a spoonful of this material would outweigh mountains. Despite this incredible density, some neutron stars spin with astonishing speed. The fastest known turns more than 700 times each second, tens of thousands of rotations per minute. At its surface, space itself moves at nearly a quarter of the speed of light. Any faster, and rotation would overcome gravity, peeling material away into space. Physicists call this the mass shedding limit, the point at which rotation can no longer be contained. Even quantum forces inside neutron stars, the pressure that prevents matter from compressing further, cannot resist infinite spin. If pushed beyond stability, the star would deform, flatten, and eject mass until equilibrium returned. Observations from space telescopes show that the fastest spinning neutron stars bulge at their equators and flatten at their poles, letting astronomers test relativity in nature's most extreme laboratory. But even these stars are not the final. Word on rotation, black holes can spin faster still. A rotating black hole, described by the Kerr solution to Einstein's equations, does not simply rotate like a solid object, it drags spacetime itself around with it. Near the boundary lies the ergosphere, where nothing can remain still, because space is pulled along by the hole's rotation. The speed of a black hole is described by a parameter where 0 is non-spinning, and 1 represents a theoretical extreme. But nature limits even this. Beyond a certain threshold, excess rotation is shed as gravitational waves or energy carried away by magnetic fields. Some supermassive black holes spin near that limit, their surrounding disks heating to tens of millions of degrees while light orbits repeatedly before escaping. These are places where space and time bend into circular paths, where geometry itself begins to twist with motion. Yet even here, nature never allows infinite rotation. As mass merges, spins combine and then slow, releasing energy into ripples in space-time, just as observed in gravitational wave detections from merging neutron stars. On every scale, from planets to dust small bodies, the balance holds. Jupiter rotates so quickly that it bulges noticeably. Spin it much faster than its equator would drift outward. Some asteroids rotate near their limits, loose materials sliding toward their edges under centrifugal stress. The rule is universal: rotation can increase only until binding forces lose their grip. the fastest spinning neutron stars define one boundary. The most extreme black holes mark another. In between lies everything nature allows. Beyond those limits, objects cease being matter as we know it and dissolve into motion shaped purely by geometry. The universe permits speed, but only up to the threshold where structure breaks. These limits are not constraints, they are the reason structure exists at all. Without them, nothing would hold together long enough to form stars, planets, or galaxies. So how fast can matter spin before the universe says no? Just short of the point where it stops being matter at all. Beyond that threshold, you leave the realm of objects and drift into a domain where motion alone sculpts space-time. You float back into stillness, carried by the quiet knowledge that even the most extreme forces in the universe obey balance. Everything spins, but only as fast as existence can endure. Sleep now, held gently by the same laws that bind galaxies together. You imagine an electron as a tiny sphere turning in space, a miniature planet rotating through the quantum void. It feels like the right picture, yet it isn't. Not fully in the quantum world. Spin carries the language of rotation, but it is not motion in space, the way a planet turns on its axis. It is a built-in property, something a particle simply is, not something it does. Just as charge determines how a particle meets electric fields, and mass determines how it falls under gravity, spin governs how it behaves in magnetic and quantum interactions. Physicists call it intrinsic angular momentum. But unlike a spinning wheel, you cannot slow it, stop it, or make it rotate faster. Its value is fixed, existing only in exact steps rather than smooth variation. For electrons, protons, and neutrons, that value is 1/2 of a fundamental constant. For photons, it is 1. For particles like the Higgs, it is 0. These values define a particle's very identity in the quantum universe. To understand how strange this is, you first recall how spin behaves in everyday physics. A rotating object can turn at any speed. Its angular momentum can slide along a continuous range of values. But in the quantum world, angular momentum comes only in indivisible unit-Steiny increments that cannot be split. This realization emerged from an elegant experiment a century ago. In 1922, 2 researchers sent a stream of silver atoms through a magnetic field, expecting the atoms to scatter across a screen in a smooth spread. If their internal magnetic orientations varied continuously, the pattern should have been a blur. Instead, the beam separated into 2 clear points, no gradient, no in-between. The atoms aligned either one way or the opposite way relative to the field. This was the first direct evidence that spin is quantized, not continuous. A binary choice, not a range. This discovery became one of the foundations of quantum theory. Spin soon revealed itself as the reason matter has structure at all. The rule that no 2 electrons in an atom may share the same full quantum state comes directly from their intrinsic spin. Without that rule, electrons would collapse into the same orbitals, atoms would lose their layered shells, and chemistry itself would vanish. The periodic table exists because electrons refuse to overlap. Spin also connects quantum mechanics to electromagnetism. Electrons behave as if they carry tiny magnetic dipoles, fields not produced by physical rotation, but by the built-in nature of spin. The strength of this magnetic moment can be calculated to extraordinary precision. and experiments have confirmed the value to more decimal places than almost any other prediction in physics. Few matches between theory and measurement are so exact on a larger scale. The alignment of billions of electron spins gives rise to magnets, an everyday reflection of a microscopic quantum property. In deeper theories, spin emerges from symmetry. Each kind of particle corresponds to a mathematical representation of space-time itself. Particles with spin 0 form scalars. Particles with spin 1/2 form fermions, components of matter. Particles with spin 1 form bosons, carriers of forces. The boundary between what is built and what binds arises from spin alone. We rarely observe spin directly, but its fingerprints are everywhere. The polarization of X-rays from dense stars, the shaping of magnetic fields in galaxies, the patterns of radiation from distant quasars, each reflects countless microscopic spins. Working together across cosmic scales, the smallest motions echo. Into the vastness, spin also lies at the heart of quantum entanglement. When two particles interact and drift apart, their spins can remain linked so tightly that measuring one instantly defines the other, no matter the distance between them. They share a single combined spin state, a connection stretching across space. This is not the rotation of objects, but the rotation of ROPs, probabilities. Modern quantum computers rely on these principles. Their qubits often come from spins of electrons or atoms, able to exist in multiple spin states at once until observed. Precise magnetic fields and microwave pulses guide these states, allowing calculations that classical computers cannot perform. This is where the difference becomes clear. In everyday physics, rotation is motion through space. A wheel, a planet, a star spinning in measurable ways from any direction. In quantum physics, spin does not describe motion at all. It describes identity. It tells you how a particle transforms when the universe itself shifts around it. It is a kind of rotation, but not of matter, of the underlying fabric of quantum reality. In quantum mechanics, something strange happens when you try to measure spin. If you choose one direction, say, the vertical axis, every other possible orientation becomes undefined. Not because the measurement is incomplete, but because the universe itself refuses to assign a definite value all at once. In the early days of quantum theory, one physicist expressed this idea with unusual clarity. He showed that spin isn't a tiny rotation waiting to be observed. It's part of the particle's identity. Not something an electron does, but something an electron is. That insight remains one of the deepest truths of the quantum world. Spin determines a particle's nature. Particles like electrons, neutrons, and protons with half-integer spin form the building blocks of matter. Particles with whole number spin, such as photons and gluons, create forces and carry interactions across space. What clumps into structure and what travels freely through space depends on this divide. So when you ask how quantum spin differs from classical rotation, the answer is gentle but profound. It is not rotation at all. It is intrinsic angular momentum without motion through space, a geometric quality written into the math of space-time itself. It tells particles how to interact, how to combine, and whether they can coexist in the same state. Though you never see spin directly, its influence stretches from electrons in atoms to magnetic fields that thread across entire galaxies. From the tiniest quantum identity to the turning of stars, the theme remains motion, even when hidden. Shapes structure. Soon, you pull back to see every layer of rotation together, from the quantum to the cosmic. A final question rises. Is angular momentum the quiet constant behind every structure in the universe? Imagine the cosmos without spin just. For a moment, atoms would collapse into uniform states. Planets would never form. Galaxies would unravel. Even time, as you know it, would unfold differently. Angular momentum is more than motion. It is the architecture of reality across all scales. From particles to clusters of galaxies, it never disappears. It connects quantum mechanics with gravity and the celestial dance of worlds. Motion may transform, but the total amount remains. At the atomic scale, this principle creates stability. Electrons circle nuclei with orbital angular momentum while also carrying their intrinsic spin. That half unit of built-in identity that prevents electrons from collapsing into a single state. Without it, chemistry would dissolve, atoms would lose structure, and matter as you know it would vanish. Each orbit and spin carves out magnetic fields that shape electron shells, the invisible blueprint of the periodic table. It is why elements differ, why atoms bond, why matter forms shapes instead of chaos, climb upward in scale, and the pattern continues. Planets form from rotating clouds of gas, conserving angular momentum as gravity pulls them inward. Young stars are surrounded by swirling disks where dust flattens into orbits rather than falling directly into the center. In these disks, collisions build worlds while motion resists collapse. Our solar system is a fossil of that early spin. Nearly all the mass lies in the sun, yet the planets carry most of the momentum, circling in the same direction inherited from that ancient cloud. Planets themselves are shaped by rotation. Fast-spinning worlds bulge at the equator, guiding winds and storms. Earth's rotation anchors its seasons, supports its magnetic field, and shelters the atmosphere from solar wind. Rotation gives worlds their climate, their shape, their rhythm. Stars follow the same rule. As clouds collapse, rotation increases, forming flattened spheres of plasma. When a massive star dies, its core contracts and spins faster, sometimes creating neutron stars that rotate hundreds of times per second. If they spun faster still, they would tear apart under their own motion. Even black holes retain this momentum. The geometry around a rotating black hole twists space-time so strongly that nearby matter is dragged along with it. Accreting gas forms, spirals of plasma that radiate energy as they fall inward, tracing the same ancient law. Angular momentum is conserved. Galaxies obey it too. Spiral arms rotate in long, nearly uniform sweeps, balanced by gravity and the unseen mass surrounding. Then, these motions reveal dark matter itself, showing that stability requires more mass than starlight provides. Across the universe, rotation holds structures together. Angular momentum binds atoms. It sculpts worlds. It stabilizes galaxies. It is the single thread connecting the smallest scales to the largest, a bridge between quantum law and cosmic architecture. Even the birth of the universe carries faint traces of this motion. Tiny variations etched into the early cosmos, measured in the afterglow of creation. whisper that rotation has shaped structure from the first moments onward. Angular momentum is not just one law. Among many, it is the quiet symmetry that keeps reality from falling apart. You settle into stillness, letting the world fade beneath a slower rhythm. And as your breath softens, you drift into a space where motion itself becomes a quiet guide. Not loud, not forceful, but woven into the fabric of existence. Tonight, you explore a universe where movement isn't merely something that happens. It's something that is done in the quantum world. Even the smallest particles are shaped by this truth. When you measure the spin of an electron in one direction, its orientation in every other direction dissolves into uncertainty. Not because anything failed, but because this indeterminacy is built into the rules of reality itself. Physicists long ago realized that spin is not a rotation in the classical sense, not a particle twirling like a tiny planet, but a fundamental, indivisible property, a quality that exists even when nothing visibly turns. One early pioneer of quantum theory once remarked that spin is not a behavior, but an identity. Something the particle is, not something it performs. This hidden angular momentum is what distinguishes particles that build matter from particles that carry forces. Electrons, those with half-integer spin, belong to the family that forms everything, solid and tangible. Photons, with whole number spin, do not collide or compete for space in the same way. They merge, overlap, and travel freely, becoming the messengers of interaction. What gathers together and what slips through space is decided by this difference. Spin is discrete, innate, and unchanging. It shapes how particles behave, how they bond, and whether they can coexist. And although you never see it directly, its influence reaches from the smallest scales of matter to the largest structures ever imagined. From the alignment of electrons in an atom to the magnetism of colossal galaxies. Across every scale, motions, sometimes silent and unseen, defines structure. As your awareness drifts further outward, you begin to see another layer. Angular momentum connecting everything from atoms to stars. If the universe were to pause its turning even for an instant, if every rotation, orbit, and spin were to fall, still the scaffolding of reality would dissolve. No atoms, no planets, no galaxies, and perhaps not even time unfolding in the familiar way. Angular momentum is not simply motion. It is the quiet architect of form. From subatomic particles to vast galactic clusters, this momentum persists. It can shift, stretch, and redistribute. But it never disappears. Within the atom, electrons carry both orbital motion and intrinsic spin. Together they create the magnetic structures that define the periodic table, each element shaped by invisible geometry. Without that built-in half-unit of spin, electrons would collapse into identical states, matter would flatten into uniformity, and chemistry would fade into silence. The world remains layered and complex because rotation grants separation, identity, and structure. As you float through this imagined cosmos, you watch the same principle appear again on larger stages. Planets form not from random chaos, but from clouds of gas slowly rotating under gravity's pull. As these clouds collapse, they spin faster, flattening into disks with young stars at their centers. Within those disks, dust grains merge, settling into orbits rather than plunging inward. It is motion that resists collapse, a subtle balance between falling and circling. Even our own solar system carries this ancient signature. The Sun holds nearly all the mass, yet most of the angular momentum lives in the planets, a memory of the cloud from which they formed. Every orbit and axial tilt is a remnant of that beginning. Rotation shapes worlds. Giant planets bulging at their equators, storms spiraling along atmospheric bands, seasons unfolding through steady tilt. Even Earth's magnetic field, the shield protecting its atmosphere, arises from the restless movement of molten metal deep within. Stars, too, are sculpted by motion. They spin as they form, then accelerate dramatically as they collapse. A star shrunk to the size of a city becomes a neutron star, turning hundreds of times per second, pushing the limits of matter itself. If such a star rotated even faster, it would tear apart under its own speed, and when collapse goes deeper still, into a black hole, rotation doesn't vanish. It reshapes space-time. Around a spinning black hole, space itself is dragged into motion, twisting light, matter, and time. Galaxies follow the same rule, rotating as vast, coherent systems. Their orderly spins reveal something hidden, an unseen mass binding them together. This pattern of motion helped reveal the presence of dark matter, the invisible framework supporting galactic structure. Everywhere you look, stability arises from rotation. Angular momentum prevents collapse, holds stars in orbit, and balances gravity's pull across scales. The rule echoes without exception. Even the early universe carries faint traces of rotation. Tiny directional patterns in the oldest light suggest primordial twists, unimaginably subtle, yet powerful enough to seed the formation of galaxies. Without those slight imbalances, matter might have spread thinly and evenly, never gathering into stars or clusters. Spin didn't just organize the universe. It remembered how every interaction, every collision, every moment of gravitational pull leaves a record in angular momentum. Two merging galaxies exchange it, flinging arcs of stars outward. Binary stars gradually synchronize, conserving the whole even as their individual motions shift. In laboratories on Earth, the same truths appear in miniature electrons, revealing discrete spin states, protons carrying aligned angular momentum into high-energy collisions, even particle accelerators accounting for spin when calculating total energy. The rule holds in quiet atoms and in roaring quasars alike. Angular momentum is not a single phenomenon, but the one thread that ties them all together. If you removed spin from the laws of physics, matter would collapse, orbits would fail, galaxies would unravel into drifting clouds. There would be no structure to witness, and no time in which to witness it. Spin doesn't just endure, it creates. It gives form to emptiness, pattern to energy, permanence to motion. From electrons to nebulae, the universe keeps turning, and every turn carries the memory of its past. The cosmos is not still. It is forever unfolding through rotation, and now, as you drift into sleep beneath the same sky that carries these quiet motions, pause for a moment in that gentle thought. Order is not born from stillness, but from motion that never ends. A soft, enduring rhythm written into the laws of existence. Tonight, may that cosmic turning guide you into rest. May your mind settle like dust circling a star, finding its natural orbit. May sleep arrive slowly and deeply, as calm and inevitable As the universe continuing to turn. Rests now. You belong to the same quiet motion that holds the stars together. Sleep softly in the gentle rotation of the cosmos.